Welcome everyone. In this video, we will solve a GATE 2004 question which is based on the rectifier in which we have to find out the peak inverse voltage and DC voltage. So the question is in a full wave rectifier using two ideal diodes. So two ideal diodes is given. So it means it is our center tape full wave rectifier, not bridge. Okay, in bridge four diodes are used. So we have to identify that this one is our center tape rectifier. Then VDC and VM the DC and peak values of the voltage respectively across the resistive load. Okay, and PIV is the peak inverse voltage. So we have to find out the correct relationship for this rectifier. So we have already identified this one is our center tapped full wave rectifier. Okay, because it uses two diodes. So that thing we have to know. Okay, so center tape rectifier is there. So I am just making a center tape rectifier. If you know the direct formula, you can also solve this question, but I am doing by proving all these parameter how we have to find the value of PIV and what we can say the VDC. Okay, so this one is somehow our say D1 and D2 diode and plus or minus V naught. Okay, okay, plus or minus Vs. And here I am saying this voltage is plus or minus Vn plus or minus Vs. Okay, so this one is our center tape full wave rectifier. Now, what we have to find? We have to find the value of PIV, okay, and the value of VDC. Okay, these two things we have to find. So, what we have to do first, if we are giving a signal, input signal, okay, like that I am writing in terms of t, or better to write in terms of omega t, or we can also write as theta. Means this one is our Vs equals to Vm sin omega t. Vm sin omega t. Okay, we are getting the secondary side voltage, that is our Vm sin omega t, or we can write as Vm sin theta t, sin theta, anything we can write. Okay, so the corresponding output waveform for a full wave, we all know the full wave output will be like that and like that. Okay, clear? This one is the output voltage with respect to omega t or theta, we can say. And this one for the full wave rectifier, I am writing full wave rectifier. Okay, and for half wave rectifier, omega t or theta, if we write only the first half. Okay, and say this one is our pi, 2 pi. Okay, pi, 2 pi, pi, and this one is our 2 pi. Okay, so this one is our half wave rectifier. Okay, so this we know. Okay, so what we have to find? We have to find the value of VDC and PIV. So VDC value, the value of VDC can be find by taking the area under the waveform. Area under the output waveform. I am writing area. This one is our D under the output waveform by the by or ratio by period of the waveform. Okay, VDC area under the output waveform. For example, suppose I am just doing for the half wave rectifier. Half wave rectifier. Okay, so in this half wave rectifier, the VDC, we have to find this area. Oh, sorry, half wave, this area. Okay, up to this range to this range. So what we can say, we can write like that: 0 to 2 pi. Okay, and then we can write as Vm sine theta d theta by the period of the signal, that is our 2 pi. Okay, by taking this elementary area d theta. Okay, directly we can write 0 to 2 pi Vm sine theta d theta, where we can write this as a 1 by 2 pi 0 to pi Vm sine theta plus pi to 2 pi. In the pi to 2 pi range, it is 0. So better to write it 0 d theta, and here also d theta will be there. Okay, so this integral will be 0. So the value of VDC will be 1 by 2 pi Vm. I am taking common Vm sin theta integration cos theta pi to 0. Then we can write Vm by 2 pi. Also I am taking minus as a common. So we can write it cos pi minus cos 0 degree. Okay, I am taking minus sign out. Okay, so this one will be minus Vm by 2 pi, and cos pi value is minus 1, so it should be 2 Vm by 2 pi. So it is value will be simply our Vm by pi. So it is means most of the people know the formula directly. So how it is coming? VDC Vm by pi for half wave rectifier. Okay, but in case of full wave rectifier, both areas should be added, a1 a2. Okay, so we can write VDC for the full wave rectifier. Directly we can write twice times of Vm pi, 2 Vm by pi, 2 Vm by pi. So VDC for the full wave rectifier is 2 Vm by pi. I am not doing this part. You can also do for the full wave rectifier by making this formula. So full wave rectifier, you have to just add this area into 2 times. Half wave rectifier into 2 times. So twice Vm by pi is the DC value for the what? Full wave rectifier. It may be either center tap or bridge. It may be for center tap or bridge rectifier. Center tap or bridge. Okay. So the value for the VDC 2 Vm by pi. Just we have to multiply by 2. Okay, because we are two, these two area we have to add together. So it is simply 2 Vm by pi. So it is very simple. Now the other thing is our peak inverse voltage. So peak inverse voltage. So I want to give you the basic peak inverse voltage. That is our PIV. So peak inverse voltage is the maximum reverse voltage that a diode can withstand. Can withstand. Okay, so now, so for this purpose I'm just making the center tap transformer. Okay, okay, so now this one is our diode. Okay, one diode is there and one more diode is there. Okay, and there is be the load. Okay, say this one is a RF and D1 and D2. Okay, and for the this purpose we are giving the negative voltage across the diode. Okay, say minus Vm, and then again it should be our minus Vm. So this, in this case, the D2 will become on, D2 will become on, and this output voltage is same as that of Vm. Okay, by applying Kirchhoff's voltage law in this loop, we can write Vm minus V naught equals to 0. So V naught equals to Vm. Okay. So now we have to think about the peak inverse voltage. So peak inverse voltage is the maximum reverse voltage that a diode can withstand. So in this case, what we have to do, we can directly replace this diode D1 with a voltage, okay, negative voltage, like that. That is our reverse voltage, PIV. Okay, negative voltage, and this voltage, that is our, sorry, we have to give the negative voltage, so it should be our Vm, and load value will be our plus minus Vm. Okay, in this case we have to just replace this one, this diode, to some voltage, that is our VPIV. Also we can write is a plus and minus. Okay, plus and minus reverse voltage, maximum reverse voltage that a diode can reach. So minus plus we have to write, and this voltage is Vm. So just apply Kirchhoff's voltage law. Okay, so the same thing I have made here. Okay, so the KVL we have to write minus Vm in this one, minus Vm, then should be minus plus, so plus VPIV minus Vm equals to 0. So VPIV equals to twice Vm. So peak inverse value will be twice Vm in case of center tap. Okay, in case of center tap it is twice Vm. In case of bridge, in case of bridge, the VPIV value will be Vm. Okay, so now we have to go to the option. So the in the full wave rectifier using two diodes. So this one is center tap. So VDC will be 2 Vm by pi for any center tap. Okay, so these two options are there for 2 Vm by pi. Okay, and PIV for the center tap is 2 Vm. So option B will be the correct answer. So option B is the correct one. This one is correct one. Okay, clear. So this is all about this question. So thank you for watching this video.